class period. Chapter 17 is all about non-specific immune system. Innate, non-specific immune system. So, like the name says, this is a non-specific immune reaction or immune defenses your body has. Non-specific means that we are not using antibodies. Any sort of out and away. Where is out and away? Sneezing, coughing, things of that nature. Cool. That is one way that we can get rid of mucus. So somewhere nearby is going to receive the signal. So autocrine, obviously, super close. I'm talking to myself. Paracrine, I'm talking to cells in my immediate vicinity. Endocrine, I'm talking to cells way down the street. Class period. Chapter 17 is all about non-specific immune system. Innate, non-specific immune system. So, like the name says, this is a non-specific immune reaction or immune defenses your body has. Non-specific means that we are not using antibodies. Any sort of pathogen that comes across this particular part of the immune system is going to be treated the exact same. There is no memory of encountering this pathogen. So it doesn't matter whether this particular pathogen I'm exposed to today or 2 years from now. Your innate immune system is going to have the exact same reaction. The innate immune system is kind of like a fence. Fences keep most things out, but also like fences, they're not indestructible. You can hop a fence if you really wanted to, or you could, break it, bolt cutters, whatever. There are ways to get around the innate immune system the same way that there are ways to get around a fence. They're great at protecting things and keeping things out, but you can still get in there if you really wanted to. Cool. The book and most people try to put the innate immune system into categories. The three major categories are physical defenses, chemical defenses, and cellular defenses. Now, are there overlaps in between these sections? Yes. So don't think of them as like rigid boxes. They're kind of fluid. Physical defenses are going to be things like physical barriers. Your skin and mucous membranes are great physical barriers, stopping or trapping microorganisms from getting into the body. Mechanical defenses, so moving or something's moving, skin cells being sloshed off, mucus being moved out and away from the body. And then your own microbiota, so the organisms that are living on you can act as a physical barrier. If an organism is already occupying a space, another organism can't get up in there. So those would all be considered physical barriers. This is just the overview. I promise we're going to talk about these more in detail later. Chemical defenses are going to be some sort of substances either produced by you or produced by the microorganisms that live in and on you. Cellular defenses, we are going to talk about the next time I see y'all. These are cells that are actually going out and handling business, doing some sort of attacking. So physical barriers, just like a way to stop pathogens from getting in and taking hold, colonization or infecting. Chemical defenses are ways to chemically inhibit growth. And then cellular defenses are when cells get in there and start messing stuff up. Again, we're going to talk about all that in detail. That was just a very quick overview. Okay, physical barriers. So physical barriers means just some physical thing that is stopping a pathogen from getting in, colonizing, and causing infection. Your skin is going to be the first line of defense in that. So your skin cells are held together through cell-to-cell junctions. There are 3 different types of cell-to-cell junctions. They are tight, desmos, and gap junctions. Tight junctions, the ones we talked about in Unit 3 with the hyaluronic acid. So there's some sort of protein that is holding those cells together very tightly. Having that protein hold cells together very tightly makes it really hard for a pathogen to get in. They have to have some sort of enzyme or a protease to break down that protein that's holding those cells together. Cool, we already talked about that one. Desmos is basically a corset or like a shoestring where you have proteins that are like holding cells together like your shoelace. And then gap junction is just a channel. So like a protein that is a channel through one cell to another cell. All of those are holding cells together tightly, keeping the good stuff in and the bad guys out. Only way, or one of the only ways that a pathogen could get in through the skin is they need to have some sort of protease, which we talked about already. Protease is going to be an enzyme. We know it's an enzyme because it ends in ASE. It's some sort of enzyme that is going to break down proteins. The proteins being the stuff that is holding those cells together. Either the hyaluronic acid for tight junctions, the shoestring, corset string proteins for desmos junctions, and the channels for gap junctions. That's one way a pathogen could get in. Another way is if you just like have some sort of skin breach. You scrape your knee, you cut yourself. Cool. So skin is a cool barrier. Why? We have these tight or cell-to-cell junctions that are keeping pathogens out and keeping the good stuff in. However, if I have a protease or though that skin is breached somehow, pathogens can get in. Another thing about skin is that it has 3 different layers, which you already talked about, but this is not anatomy class. The only one we care about is the dermis. The dermis has several different layers. Most of it's dead skin cells. Cool. So the dermis is made up of a whole bunch of dead skin cells. Those dead skin cells are going to get sloshed off. A whole bunch. So if I have dead skin cells that are constantly being sloshed off, it's going to be real hard for pathogens to get up in there to attach and then cause infection, right? If something is constantly being sloshed off, pathogens cannot get up in there. The skin also has a lot of acidic compounds and fat. This is going to make the skin salty. What else was I going to do? I wrote something down. Hold on. I lost the line. Salty and dry. Salty and dry. Salty and dry is not favorable environments for microorganisms. As y'all have learned in lab, hopefully. Most of the organisms that we would come into contact with that would cause disease don't like it real salty and not dry at all. So the skin being a dry and salty place makes it hard for pathogens to exist, or just microorganisms in general to exist. The other thing is keratin. This is super tough. So what makes it super tough? Enzymes, bacterial enzymes can't degrade it. Cannot be degraded by bacterial. That's ugly. That's even worse. Bacterial enzymes. Probably spelled enzymes wrong, just deal with it. So keratin is a chemical that is in skin that is extremely tough. What do I mean by it being extremely tough? It cannot be broken down by bacterial enzymes. Because it can't be broken down by bacterial enzymes, it can't be broken down by bacterial enzymes, therefore bacteria can't grow and exist there because it's taking up space. It also can't be used as a food source. So not only can bacteria not break it down in order to make space for them to be able to grow, they also can't use it as a food source. So it's double bad. Can't be broken down, so I can't clear it out to make space for myself if I'm a pathogen. I also can't use it as a carbon source. Can't use it as a carbon source, can't break it down. The skin is salty and it's dry, and I keep getting sloshed off because it's made up of so many dead skin cells. They're just constantly being sloshed away. Not a good place for me to live. I'm going to go live somewhere else. Cool. So the skin's a bad place to live because it's made up of a lot of dead skin cells. It's extremely salty and dry and has a lot of keratin. Keratin can't be used as a food source, and I can't break it down in order to make space for myself. Skin is made up of very tight a lot of tight cell to cell junctions. Because they are tight junctions held together by proteins, unless I have a protease, I can't get it. That's the gist of skin. Now we can talk about mucous membranes. So, mucous membranes are going to line certain areas of the body, specifically mouth, nose, digestive, urogenital systems. They have a lot of different uses. One of their main uses is to having that mucous membrane there is to trap debris and trap microorganisms from getting further into the body. Do those mucous membranes have other functions? Yes, they do. But one of their function is to trap debris, other microorganisms from getting into the body that aren't supposed to be there. So think about it. You breathe in through your nose or through your mouth. Your lungs are lined with mucous membranes, so that dirt, debris, spores, anything that you breathed in can be trapped in that mucus before it gets down into your lower lungs. Ooh, great. So cool. The mucus that's in my lungs or GI tract, wherever, has trapped the pathogens, the trapped bacteria, dust, debris. What am I going to do with it now? Great question. You have something that's called a mucociliary escalator, which is going to be ciliated cells that are going to move that mucus out and away from your body. So nose, move it out through your nose so you can sneeze it out. You can cough it out, can be swallowed, can be defecated out, just out and away from your body. The mucociliary escalator is the ciliated cells that are moving it out. Moving it out and away. Where is out and away? Sneezing, coughing, things of that nature. Cool. That is one way that we can get rid of mucus. Okay, cool, but what if I took the swallow route or mucus is in my stomach? How is that getting out of the body? Peristalsis. So smooth muscle contractions, smooth muscle meaning that you are not controlling it. Those contractions are going to help eliminate waste and also that mucus out and away from your body. Cool. So mucus is trapping any sort of dirt, microorganisms, debris, things of that nature. It is being moved out and away from the body after it's done all its trapping through the mucociliary escalator, which is going to be ciliated cells sweeping it away, out and away, and then peristalsis. Cool. Great. So those are physical barriers. Now we have mechanical barriers, meaning that there's going to be some sort of movement that is helping pathogens move out and away from your body. Is there going to be overlap from physical barriers? Yes, there is. Deal with it. Cool. So first one's going to be peristalsis. So the same motion that is moving urine and feces out and away from your body is also going to help move the mucus that are in those areas out and away from your body. Cool. Shedding of dead skin cells. We talked about this with physical barriers, but we get to talk about again with mechanical barriers. Dead skin cells are constantly being sloshed off. Those cells being sloshed off means that pathogens cannot infect. What's the word that I'm looking for? The one that comes before infect. Y'all just had a test on this. Before you colonize was the word that I was looking for. Thank you. Cannot colonize and then infect. Trapped in the mucociliary escalator. We already talked about this. Mucociliary escalator. Mucous membranes are lining most of the openings to your body. Along with other things, they are there to trap microorganisms from getting in and actually causing infection. New things, tear and saliva production and blinking your eyes. Blink your eyes is obviously something that you are actually doing. The blinking of your eyes helps sweep pathogens out and away from your eye. The production of tears and saliva will also move pathogens out and away from those areas. Cool. Next new point, your microorganisms. Like I said a couple of slides ago, the normal microbiota that actually lives in your body, that is supposed to be there to make vitamins and minerals for you, live in your body. So they don't want a pathogen to come in and wreck shop. Why? They're already living there. So if they're living there, they're not trying to have to compete with a pathogen. They already set up shop. They like the house that they're in. They don't want to get kicked out. So by them just being there, they already occupy that space. So they're already out competing the pathogen because they already live there. They've already set up shop. There's no space for them. If the pathogen had some sort of antimicrobial agent or was trying to compete, your microbiota is equipped with certain chemicals, which we will talk about in the next slide, to try to kill that pathogen. Because again, they live in your body too. So they are going to use their defenses to defend where they live, like any normal organism would. Cool? So your microbiota is going to use its abilities to defend itself. By them defending themselves, they help defend you. Cool. This point here about antibiotics. Remember when we talked about with Unit 3, if you overuse antibiotics, you can kill the good and the bad bacteria. If you kill the good bacteria, bad bacteria can't get in and wreak shop, which is not great. Cool. Great. Chemical defenses. This is where I have to start writing things down. So, with chemical defenses, you're going to be talking about chemical mediators. So, chemical, because I'm going to spell it wrong, mediators. These are substances found in tissues or bodily fluids that inhibit bacterial growth. So chemical mediators are going to be substances that are either found in tissues or in bodily fluids that are going to inhibit, aka stop, bacterial growth. There are two types that we care about. They are either going to be endogenous or exogenous. Because I'm going to spell it wrong. EOUS. Or exogenous. No. Genius. Endogenous is going to be made by humans. So made by humans, made by human cells. Exo is going to be made, nope, put it backwards. Made by bacteria. Cool. So chemical mediators are going to be any substances that are going to inhibit, aka stop, bacterial growth. Under that, we have two different types that we care about, endo and exo. Endogenous is going to be made by human cells. So examples of that is going to be sebum, saliva, stomach acid, anything that your pancreas makes, tears. So in sebum, there are different chemicals that are sebum's made by cells by your hair follicles. So there are chemicals in that stop fungi, mostly, and other bacteria, but fungi, from growing. There are chemicals in saliva. So you have lactoperoxidase and lysozyme. You're going to hear a lot about lysozyme from now until the end of the semester. Those enzymes are going to help degrade bacteria and stop bacterial growth from happening. More lysozyme in tears. Cool. All of those are made by humans. Because they're made by human cells, they're going to be endogenous. All right? Exogenous. Anything that is made by bacteria. So, the lactobacillus in the female reproductive tract lowers the pH. Lowering the pH means that things like yeast won't grow there because the lactobacillus is what's causing the pH to change. It's exogenous. Exo meaning like out, not human. Cool. Does that make sense? So these are all chemical defenses. What makes them chemical defenses? These are substances that are stopping bacterial growth from happening. If it's made by human cells, it's endo. If it's made by bacteria, it's exo. Sebum, saliva, earwax, tears, enzymes made by your pancreas. All of those are made by human cells, endo. Anything made by a bacteria is going to be exo. Cool. We're going to come back to this slide later. Okay. So now we have to talk about the complement system, the complement cascade. This is one of the things that kind of straddles the line between the adaptive, which is your immune system that has memory. The adaptive immune system has memory. And your innate immune system, the one that doesn't have memory, aka the one we're talking about right now. So this complement system is a slew of different plasma proteins. I almost forgot what the word plasma was. This is a lot of different plasma proteins that are always constant in your bloodstream. Because complement proteins are always present in your bloodstream, we consider it part of the innate immune system because those proteins are always present no matter whether there's a pathogen there or not. So there's something that they're just always there floating around. At the end of this complement system, we are going to be making membrane attack complexes. Those membrane attack complexes are going to help your immune system attack pathogens. Okay? There are 3 different ways I can start this cascade. These 2, which I'm going to talk about more in detail in a second, are both innate activations. This guy right here is an adaptive activation. So out of these 3 ways that we're going to talk about activating this complement cascade, only 2 of them belong in the innate immune system. 2 of them belong in the innate immune system. This one right here belongs in the adaptive, but we're going to talk about them all at once. Okay? What's up?
Would we be tested on the second one since it's adaptive?
Yes, because we're going to talk about the adaptive immune system, but like chapter 17 is the innate, chapter 17 is innate, 18 is adaptive, and then I forgot what 19 is because I kind of just slide through that one real quickly and just say, hey, this is what's going to be on the test. Moving on. Cool. All right, so the whole purpose of the complement system is to help defeat, what's the best word I can think of, microorganisms. The complement system is just a whole bunch of plasma proteins that are constantly in your bloodstream. Eventually they are going to make membrane attack complexes, and there are 3 different ways that I can start a cascade happening. We're going to talk about number 1 first. Number 1 is the alternative pathway. This is when a complement protein called C3 is going to bump into a pathogen. C3 bumps into a pathogen, it is then transforms into C3b. Once that C3b and that pathogen, they attach, we're going to move down the complement cascade. Now I'm going to show you a slide. It's going to be real scary. Don't get scared. So here's the alternative pathway. So C3 over here is chilling in your bloodstream. It's always there. It is going to spontaneously flip back and forth between C3A and C3. Just back and forth. However, if it bumps into a pathogen, it is going to turn into C3b. After that, we move down the complement cascade to make membrane attack complexes. Do you need to know the different C's and all of that junk? No. What I want you to know is that, hey, there are 3 different pathways that I can go through to activate the complement cascade. One of them happens to be the alternative pathway. What happens in that pathway? C3 bumps into a pathogen, it becomes C3b, and then we move down the complement cascade to make a membrane attack complex. We'll talk more about this in a second. Do you need to know that what these C's are? No. Okay? Yes.
What's the spontaneous activation to C3A?
So C3 is literally, it's chilling your bloodstream, right? And while it's in your bloodstream, if it's not bumped into a pathogen, it will flip from C3 to C3A and back and forth, back and forth, back and forth. It's just vibing. It's just living its best life. However, if C3 bumps into a pathogen, it's C3B, and then it's game on. We're going down a complement cascade. Cool. So C3, living his best life, flipping between C3 and C3A. But if a pathogen shows up, they bump in together, we are now C3B, and we move down the complement cascade to make membrane attack complexes. We'll talk more about membrane attack complexes in a slide. Give me a second. Okay? That is one way I can make a complement cascade. There are two other ways, but that's the first way. Okay. The second way is the classic way. The classic way involves an antibody. Antibodies means that we have some sort of memory. The innate system does not have memory. The adaptive one does. So we are only going to see the classic pathway in the adaptive immune system. Why? Because it involves an antibody. Okay? So what happens is antibody binds with an antigen. When antibody binds with antigen, they make a complex. Antibody, antigen bound together. That complex, is going to bump into C1. Once this complex bumps into C1, we move down the complement cascade to get membrane attack complexes. Do you need to know the different C's we went through in order to get there? No. I just need you to know that the classic way to trigger a complement cascade is to have antibody antigen bind together. That bound antibody antigen complex is going to bump into C1. How do they bump into C1? Complement proteins are always in the bloodstream. Cool? There's like 30 of them. They're always there. Once that complex binds or bumps into C1, complement cascade. Cool? That is the second way we can activate a complement cascade. All right? The third way is the lectin way. So, during some sort of bacterial infection, because I don't want to say the wrong organ, your liver is going to start producing lectin. That lectin production is going to bump into or come into contact with C4. Once lectin binds with C4, complement cascade. Right? So those are three different ways I can make a complement cascade happen. Through the alternative pathway, where a pathogen bumps into C3, becomes C3B. Classic way, antibody antigen binds with C1. Lectin binds with C4. Now, someone asked the question, well, if this one happens, do the rest of them happen? Not necessarily. If this step happens, does that mean you can't go back and have this step? Not necessarily. They kind of happen independently. If this is your first exposure to a pathogen, your innate immune system is going to be the immune system that is taking on the brunt of that role. Your body has no memory of it, therefore no antibodies. So you are going to have a lot of alternative pathway activation of complement proteins. If this is a pathogen that you haven't encountered before, you're going to see less of the alternative pathway and way more of this one because you have antibodies for that particular protein or pathogen. Cool? So again, if this is like a new pathogen, a new bacteria, then your liver is probably going to be producing a lot of lectin. Why? Because you don't have any help from antibodies. So you're probably going to see these two more for a new infection, a pathogen that you've never seen before, your body has never experienced before, and none of this one. If you had this pathogen before, you're going to see a lot of this activation, a lot of classic, and less of these. Okay. I could care less about the things in the middle. I care more about how it starts and the end. Okay? There's a whole bunch of detailed stuff in this unit. I'm not getting detailed about that. I'm going to get detailed about other stuff that matters. Cool? Great. So, cool. The complement system cascades. What's the purpose of that cascade? Great, I would love to tell you. So at the end of the complement cascade, you're going to have 3 different results. You're going to have opsonization, you're going to have inflammation, and you're going to have cytolysis. So the end of the complement cascade, its goal is to have opsonization happen, inflammation, and cytolysis. Do you need to know the C's that go into these things? Absolutely not. Ain't nobody got time for it. I want you to know these things and why they're important. And I will talk to you about that right now. So what is opsonization? Opsonization is when you have proteins that are called opsins that are going to label your foreign pathogen. So they're going to tag, label, mark the pathogen to let the phagocyte cells know that, hey, this guy's a problem, go Pac-Man them. Phagocytes go in, chomp. How do the phagocytes know who to attack? Opsonization. Complement proteins are going to go in and label that pathogen. Say, hey, phagocyte, chomp that one. Cool. So opsins are going to be complement proteins. What are opsins? They are complement proteins that label the pathogen. Why is the pathogen being labeled? So that the phagocyte knows who to go chomp down on. That is one of the outcomes of the complement cascade. Inflammation is another one. Inflammation is fluid going to the infection site or that area. Why do I want more fluid there? Because neutrophils and other white blood cells are the guys that are going to be doing the killing of the pathogen. Either the chomping, the killing, the neutralizing of the threat. Having fluid head to that place makes it easier for those white blood cells to get there because they're big, chunky boys. So inflammation means that more fluid goes to the area of the infection. That fluid moving to that area is going to make it easier for the white blood cells and neutrophils to go to that area and neutralize the threat. White blood cells are big cells. They need fluid in order to weasel their way through to the infection site. Cytolysis. Cyto meaning cell, lysis meaning to cut. So you are going to have a complement proteins that are going to help communicate, hey, I need cells over here that are going to go chop, 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 or make holes into this pathogen. Cool. So cytolysis, the making of holes, cutting up of cells. Complement proteins are going to say, hey, this guy's a problem. They're going to release chemicals that are going to cause certain cells to, or certain enzymes to punch holes into cells. Most of the pathogens that are harmful to us are typically gram-negative. So having complement proteins, have enzymes that punch holes in the gram-negative cells will go for us. Two-ish more slides, and then we're done. All right, so there it is. Bam. So we have to talk about cytokines. Cytokines are soluble proteins that are used for cell communication. I should write that down. Cytokines. Proteins. Proteins is probably spelled wrong. Don't tell me. Let's try it the other way. And they both look awful. Proteins is spelled wrong. Don't tell me. I already told you I can't spell. I have a learning disability. Don't judge me. Proteins used for cell communication. These are proteins that are used for cell communications. There are three major functions for cytokines. Three ways, three types of communications. Cool? You got autocrine, paracrine, and endocrine. Autocrine is a cell talking to itself. So the cell that released the cytokine is also has receptors on it to receive that message. So let's say we have a immature B cell. I know we're not talking about the adaptive immune system, but it works. We have an immature B cell, and it has come into contact with a pathogen. It can then release a cytokine, say, hey, it's time for us to mature up and go in and start fighting. So that is a instance where that cell is talking to itself. It will release a cytokine, and then that signal will be received by the cell. Cool? So autocrine, talking to yourself. Cool. Paracrine, a conversation, talking to another person. So one cell is going to release the signal, another cell somewhere nearby is going to receive the signal. So autocrine, obviously, super close. I'm talking to myself. Paracrine, I'm talking to cells in my immediate vicinity. Endocrine, I'm talking to cells way down the street. So think about like your endocrine system. So like your thyroid and your pituitary gland, they're like, your thyroid's like in your neck area and pituitary's like in your brain, like in the middle of it. They talk into organs far, far away. How are they doing that? They are releasing chemicals into the bloodstream, and then the bloodstream is then carrying that signal, those words, those commands through the blood to wherever it needs to go. Cool? Endocrine, you are releasing the cell signal into the bloodstream, and then that signal is being taken far, far away. Paracrine, you're talking to the people, the cells immediately around you. Autocrine, you're talking to yourself. Cool. Those are the three functions, the three ways that cytokines are used to communicate. Cool. There are three different classes. So we have three different functions, how they talk to each other, and then we have three different classes. This is a slide of just one of them. So let me get rid of that so that's not confusing. So the three different classes are, I'm gonna erase this so I can stay close to my notes. So you have interleukins are one. Interleukins, that's one type of class. Your second type of class are going to be chemokines. Your last class is the one that's up here, interferons. So these are your three different classes. You have interleukins, you have chemokines, and you have interferons. Interleukins are basically, they were thought to only be produced by white blood cells, but they are produced by other types of cells. But these are going to be cytokines, so chemicals that are telling white blood cells what to do. Really just telling white blood cells what to do. So like, more white blood cells need to be produced. I need this many types of white blood cells. I need this white blood cell to do this thing instead of this thing. Just telling white blood cells what to do. Anytime you see the word like leukins, you should probably think about white blood cells. So interleukins, white blood cells. Telling white blood cells what to do. Chemokines are telling, this is running out. I want to stay in purple. Ugh. Sorry. Telling white blood cells where to go. There we go. So interleukins are telling white blood cells kind of what to do. Chemokines are telling white blood cells and other cells where to go. What to do, where to go. Okay. Interferons are infected cells crying for help. Cool. So interferons are going to be released by infected cells. So think a cell that's infected with the virus or a cell that is like a cancer cell. So a cell that's infected with the virus is like, oh man, the virus is inside of them, taking over their machinery, making more virus particles. The cell's like, oh my gosh, I gotta do something. I don't want the other cells around me to get infected. So that cell is gonna release interferons. Those interferons are basically saying, yo, I'm infected. You gotta do something. I'm the problem, come get me. Cool? So interferons are a way for an infected cell to communicate to the cells around them, hey, I'm the problem, do something. Most of the time, it is going to tell the cells around them to do apoptosis, aka programmed cell death. Because if those cells die, then the virus has nothing to infect. Those interferons can also be interpreted, taken in by a natural killer cell or others like immune cells around them, and then those cells will deal with that cell that's infected. Okay? But interferons are released by the infected cells saying, hey, I'm the problem, you should probably do something about it. Cool. That's it. So, before you start moving, next time I see y'all, we're going to be talking about this chart that has a lot of different cells on it. And you're like, man, do I need to know all these cells? Kinda. If I talk about it in grave detail, you will definitely need to know information about it. But if you want to like get started, I would definitely think about We're going to talk about a lot, so you kind of need to know all of it. So just a heads up first. The next slide also has a lot of information, but that definitely has too much. Obviously, you can't read it off the slide, but look in the book. But you will need to know a lot of information about those cells. I'm giving you fair warning now. What I want y'all to do sometime in the not too distant future is in Blackboard now, because I just put it there. There is a Chapter 17 Part 1 worksheet. I think, and other students said that it was helpful for y'all to like have stuff to work on. And with exam 4 not being great, I think it's going to be very helpful. So the framework of how those worksheets are going to work, they're going to have vocabulary words at the top and then a couple questions at the bottom. All you have to do is like write out those definitions and then answer the questions. I will look at them sometime between now and when y'all take y'all's test, and as long as it's good, you get the grade. Cool. What questions do you have for me? Y'all have any questions for me?
It's available to us there.